Okay, so due this week of today is when the homework for chapter 8, module 8 is due. So it's at midnight tonight. So go ahead and take those last 4 slides and do, it's in that last section of chapter 8. And then we will start with module 9 today. We won't finish it today. We're probably going to not finish it until Wednesday or Friday, but that homework isn't due till the following Monday as well. Okay. So as we all see, our Zoom class is here today. And that is all I have for administration. Does anybody have any questions about that or our due dates?
Yeah, I have a quick reminder that today is the last day to get credit for your session. If you want to get that participation credit, today's the deadline. So today might be really busy. We'll see.
Okay, thank you.
I have a question.
Yes.
When is our next test scheduled for?
Our next test is scheduled for, let me pull it up here. It's in December 2nd. Okay. So we're going to do modules 9, 10, and 11, and then we're going to have an activity on November 30th. And then we're going to have exam on December 2nd. So that'll be our third exam. And then that one's going to focus on modules 8, 9, 10, and 11. And then on the comprehensive final, it'll be spread out over all 11 modules. Okay.
Is that activity after Thanksgiving break?
Correct. That activity is the Monday after Thanksgiving break. And it kind of summarizes all 11 modules together. And that way, December 2nd is a Wednesday. Yes, we'll have on the Monday, November 30th is our group activity. And then December 2nd, our exam will be on that Wednesday before the last day. Reading day, I believe, starts on December 3rd. So then our final is actually at December 7th at 11 a.m. to 1:30 p.m. Okay?
Okay, thank you.
Yeah, those numbers haven't changed. Those are still on Canvas, by the way, under lecture and exam schedule. So you can, if you didn't write that down, go ahead, you can go see them there. Okay, so I'm going to go ahead and share my screen, and you guys can type in any questions you have while I'm doing that. Let me go ahead and move my people over here. There we go. So I was rearranging my office last week and I broke my old monitor. So I have a new monitor and it's not as big. So it's not near as fun. Okay, so on Friday, we talked about how some reactions of alkynes are very similar to those of the alkenes. And it's all because we're reacting that pi bond with these different reagents. And so one of the differences we found was when you do a hydrolysis of an alkyne, instead of going to an alcohol, you end up getting a ketone out of the system, because the first step is the formation of the alcohol, but it still has one of the double bonds still available right here. And so this is an unstable form called the enol form. And with acid or base, it can rearrange to give us a ketone or an aldehyde here. So that's one of the reactions that's a little bit different than the alkenes, because the alkenes give us alcohols, and typically because of the formation of the carbocation, it gives us the most substituted alcohol. So you're looking for secondary alcohols and tertiary alcohols. Here in the alkynes, we end up with a ketone or an aldehyde. So that's one of the big differences there. Okay, and just like in the case of alkynes also undergo hydroboration oxidation reactions, and it follows the same mechanism where the boron is going to go on the least substituted side. And when we oxidize that down, it again gives us this enol form of our system, which again is unstable. And so it rearranges, and it typically, if we have a terminal alkyne, we get an aldehyde out of the system. And we get an aldehyde from the reduction of the alkane. So this is a really cool reaction. Now, To make sure that we only react one time, we use special borane reagents. Notice each of these borane reagents up here only have one hydrogen on them, okay? So it already has two alkyl groups on there, but it has one hydrogen. And we do that specifically so it can stop the reaction at our intermediate to give our vinyl borate. And then when we do our hydrogen peroxide in basic conditions, it'll form our enol, we'll get our primary alcohol on our alkene, but then of course it rearranges to give us the aldehyde. If the double bond is in the middle of the chain, it'll give us a ketone. But it's really specific that we only have one hydrogen on each of these boron reagents, and they have like 9BBN is a very common acronym for that. And the key there is that you have the boro compounds are the ones that stop at that stage, create a stable carbon boron bond until you oxidize it. And then you have to use peroxide and base to oxidize that carbon boron bond, just like we did in alkenes. We do that same thing in alkynes, but it rearranges to give us the carbonyl. Also analogous to what we see in alkenes is when we do ozonolysis, we break the triple bond. Just like we break the double bond in alkenes, we're actually breaking the triple bond in the alkynes. So if we had an alkyne where it's in the middle of the chain and we ozonize it, we end up getting two different carboxylic acids if the sides are different chains. Notice ozone does not react with sp3 hybridized carbons. It does not react with the CH2s or CH3s. It only reacts with pi bonds. And if it's only reacting with pi bonds, it's actually going to clip all the way through that pi bond. And again, it forms a similar intermediate where we have a 5-membered ring with the oxygen, but then it rearranges a little bit and displaces and gives us our 2 carboxylic acids. Now, what if you have one on the end of the chain? Do you still get 2 carboxylic acids? And the answer is yes. You end up with the long chain carboxylic acid for the one side here, but this carbon here doesn't go away. It actually turns into our smallest carboxylic acid, which is methanolic acid. It's also called formic acid. Sometimes in the text, it'll say formic acid, but it still has that carbon, has that carbonyl and that oxygen on there, and the hydrogen, notice it's still there. So we still just clip the triple bond, everything else remains intact. Okay, so that's one of the great things about ozonolysis. It only attacks your double and triple bonds. Everything else stays the same. Okay, now in the alkenes, what we did was we oxidized them with chromic acid and other things to create alcohols. But we also showed you that if you had potassium permanganate, it could actually clip chains. It could actually clip the double bond and give you 2 carboxylic acids. Okay, now in contrast to that, when we do it with an alkyne, what we end up doing is getting an intermediate where we've actually added an OH to each side right here. Notice this is at neutral pH, okay? Gives us an OH at each side here, so we have a tetra alcohol. That tetra alcohol is not very stable, and so what it's going to do is it's going to lose 1 OH here. Oops, sorry. Let's do it right here. It's going to lose an OH here and a hydrogen on this side to generate our carbonyl compound. And then the other one's going to do the same thing on this side, 1 OH, 1 hydrogen to give us another carbonyl compound. So under neutral conditions, potassium permanganate pH 7, we get a diketone compound. Okay, so this will happen when we have that in the middle of the chain. When we have it at the end of the chain, we still have this, we form this carboxylic acid, we form this carbonyl compound with an aldehyde on it. Unfortunately, that aldehyde is very easily oxidized, and the permanganate continues to oxidize it down to a carboxylic acid. So we get what we call a keto acid. So it's a carboxylic acid bound directly to a ketone. So again, this happens at pH 7, so it's a very mild reaction, but it gives us these very unusual structures. It doesn't give us carboxylic acid, it doesn't break the chain. It actually just oxidizes down the triple bond to give us two carbonyl compounds. And if it's at the end, it ends up being a carboxylic acid. If it's in the middle, it's a diketone compound. Okay. However, if we do this under basic conditions, we get a little different reaction happening. If we do under basic conditions, we see what we see in the alkenes. In fact, we break the triple bond, giving us carboxylic acids. Okay. So under these basic conditions, we end up getting it to oxidize those carbonyl, that diketone down even further to give us a carboxylic acid on one side. And for a terminal alkene, we end up with this formic acid as the salt. Okay. So at the end, at that reaction point there, they are deprotonated because we're in basic conditions here. Okay. Now, this formic acid salt here can be further oxidized down to carbonate ion, which then decomposes into CO2 and water right here. So a terminal alkyne will generate one carboxylic acid and a whole bunch of CO2 and water. In the presence of a carboxylic acid, in the presence of an internal alkene, we just end up with the two carboxylic acids. Remember, we're just breaking right here at the triple bond and giving us two carboxylic acids from the system. Okay. So what we'll end up with is however many carbons you have on the end of the chain here. Again, the permanganate does not attack sp3 hybridized carbons and hydrogens. Therefore, it has to go for the double or triple bond. Look at it attacking that pi bond, and we get very analogous reactions to what we see in the alkenes. Okay, so that's the end of alkynes there. So we did everything from deprotonating a terminal alkyne to turn it into a nucleophile. And then we did a compare and contrast with the alkenes as to see what kind of reactions if they do the exact same reactions. In many cases, they do the same reactions, like addition reactions, it'll add Markovnikovs. In oxidations, we can get to stop. However, there are some differences. For example, the hydrolysis gives you ketones and aldehydes, which you didn't get from the alkenes. So make sure you, draw the differences between these as well as the similarities. Okay? Questions on that? Okay, I'm going to switch over to my next set of slides here, which is NMR spectroscopy. Okay, so, just so you know, all of these slides are now on a Canvas all the way through the end of the semester, including chapter 11. So you can go there and see those. All my slides are also, I think, posted on Canvas as well. So all of those should be available to you. And I think I've already assigned all of the homework through the end of the semester. So those should be popping up in a regularly scheduled pattern. Okay. So now module 9. So in our module 2, we looked at IR spectroscopy. And IR spectroscopy told us about the types of bonds we have, right? So it told us that we had a carbon-nitrogen triple bond because that bond absorbed a certain amount of energy and vibrated, and therefore it was absorbing that wavelength, and we could see that in our spectrum. Okay. In NMR spectroscopy, we're actually looking at the nucleus of the atom instead, not the actual bonds, but actual nucleus of the atom, but protons and neutrons in the middle of the atom. So this is a little different. And remember, when we're talking IR spectroscopy, those bonds are electrons. Every single sigma bond is 2 electrons. Every single pi bond is 2 electrons. And so we're looking, you almost want to think of that as, oh, those are, functional group spectroscopy. Here, what we're looking at is looking at what's attached to things and looking at how the nucleus is interacting with the electromagnetic spectrum. Okay. So the basic idea is that, okay, when we talked about electrons, we said they had spin, right? Because they're moving very fast and they're spinning, and that creates a spin moment. That creates a magnetic field associated with that spinning nucleus. Well, protons and neutrons do the exact same thing. They're spinning very quickly, and they create a magnetic field, a north pole and a south pole, okay? Now, it's because they're surrounded by electrons, the individual nuclei don't sense each other, and they kind of randomly move around in the middle, and they're not really aligned at any point in time in a regular solution. However, if you were to put this in a huge magnetic field, a very high magnetic field, what happens is the nuclei, those little magnetic moments, have to align with the field or spin against the field. And it depends on how many protons and neutrons you have to say how many are aligning with the field and how many aren't aligning with the field. Okay, so when they aren't aligned with the field, this is a higher energy state, okay? Because when they're aligned against the field, they're kind of fighting that, but they're fixed in that space because the magnetic field is going in one direction only. Okay, so each individual neutron and proton in the nucleus will do this in each nucleus of each atom, okay? So how do we use that to our advantage? Okay, so we use that into our advantage in nuclear magnetic resonance spectroscopy by taking all of these spins, putting them in a magnetic field, and then taking radio waves, very long, very low energy, long waves, and hitting the solution in that magnetic field. And what that does is that interacts with that little magnetic moment and flips them up to a higher energy state for a little bit of time. Okay. And when we see that flip from that low energy state to that high energy state, we can observe that with other radio frequencies. Okay. So what we're observing is this flipping from the standard state, the relaxed state, to this excited state. Okay. Now, they do it at different amounts of time. And because different nuclei do it at different amounts of time, we can actually tell the difference between an atom with one hydrogen on it versus an atom with two hydrogens on it versus an atom with three hydrogens on it. So that we can tell these differences and we can look for those different changes. Okay, so, and then at the end of the experiment, they've all relaxed back down to their lowest energy state, and we can pulse it again and wait for it to relax, and then pulse it again and wait for it to relax. And by adding all of this information together, we get an idea of what atoms are near what other atoms. Okay, so when we're looking at proton NMR or NMR in general, we're looking at different factors that tell us something about the spectrum. In the case of proton NMR, we're looking at hydrogen. Okay, so it's hydrogen, it has one proton, and because it has one proton, it only has a half spin. And because it has a half spin, we can see it by NMR. The great thing about hydrogen is it's about 99% of all of that isotope. So it's very common, very easy to see, and we get a lot of information from these hydrogen. So when we look at proton NMR, what we're looking at is only hydrogens. We're not looking at carbons or any other atom. We're looking at only where the hydrogens are and where they show up on our thing, on our spectrum. So we need to look for four things when we do proton NMR. We need to look for the number of signals. Okay, the number of signals tells us what kinds of hydrogens we have. We need to look at the intensity of the signals, because if we add up all the area under each of these peaks, we can actually correlate the number of protons at each peak, so that each signal can correlate to a certain number of protons. Ooh, this signal has 3 protons, this signal has 2 protons, and we can see that. The third thing we need to look at is position. Position is all about the electronic structure around that hydrogen. Okay, so if you're bonded to something that's pulling electron density away, you are not, the electromagnetic radiation can see that nucleus more easily. Therefore, it moves around in our spectrum. It changes the frequency where we see it. And then the last thing, which is sometimes the most difficult, is what we call the spin-spin splitting, which means that if I have hydrogens 3 bonds away from another hydrogen, if they're not the same, they can split each other. They can make the signal go from a single peak to multiple peaks. And we'll talk about how to identify that and the patterns we normally see for those. Okay, so whenever we look at a spectrum, we want to identify these 4 things for proton NMR. Okay, so here's what an NMR spectrum would look like, okay? So on the y-axis, we have intensity, okay? It's just a relative intensity. It's not a real, it's not a measured number. And so we really don't care how high the peaks are. All we care is that all the peaks show up on the screen. The first thing we want to look at is the number of signals. Now, if we look at this compound right here, okay, the number of signals is derived by how, if they are chemically equivalent or if they are chemically not equivalent, okay? So just empirically, this carbon, these hydrogens are bonded to this carbon, which is bonded to a bromine, which is bonded to a carbon, okay? So those hydrogens are associated with a carbon that have a bromine bond and a carbon bond. Okay. Now, if we look at these hydrogens here, those are 3 hydrogens bonded to a carbon, only bonded to another carbon. So they are different. They are each going to have their own peak. Okay, they're each going to have their own signal. So that's number one, number of signals. In this compound, we predict there to be 2 signals. Okay, so that's number one. Number 2 is intensity. Okay, now again, it's not the height of the peak. It's actually, if we look at here, there's actually a lot of area under this peak. There's we measure all of this area under this peak. And if we add all this up together and compare it to all the area under this peak, we'll see that this will give us a factor of 2, and this will give us a factor of 3, telling us that we have 2 hydrogens on this position and 3 hydrogens on this position. So it's a very useful tool for helping you pick out which signal is which, because that intensity gives you the equivalent number of protons for that. Okay, the third thing we need to look at is chemical shift. So that means that we have, this starts at 0, and we're going to talk about TMS. This is tetramethylsilane. We use it as an internal standard to say that's 0, and everything is measured off of it, okay? Now notice that we have an increasing numbers over here, and these are ppms, and this is just a measure of shift, okay? So what it's saying is that the chemical environment around these hydrogens is different than the chemical environment around these hydrogens. And it's demonstrated by that shift, which means different types of chemical environments around hydrogens are going to show up in different places on this x-axis. So we're going to see that happen a lot. And then a last thing we're looking at is the splitting patterns here. And we're going to talk about why these are split into all these different things. If we had no hydrogens coupling to this, we would get a single peak for this and a single peak for that. But because we have hydrogens within 3 bonds of those, they influence the shape of the peak. And that we call that spin-spin splitting. Okay, so this is what to look for whenever you look at an NMR spectrum. And again, you're only looking at hydrogens so that you don't have to worry about carbons or anything else, but you can see that other things are there because of the chemical shift. Okay, so let's talk about number of signals. That's the first thing we need to look at. So the number of signals means they have to have different electronic environments. Okay, that's what they are. They don't have to be in different places on the molecule. If we have symmetry, they could be 2 ends of the molecule actually look identical to each other, and they would have an equivalent proton. Okay, so let's look at it from a perspective of electronic signal. Okay, so we have a CH3 bonded to an oxygen on that side. We have a CH3 bonded to an oxygen. So electronically, they are equivalent because they have 3 hydrogens on a carbon bonded to an oxygen, 3 hydrogens on a carbon bonded to an oxygen. That gives rise to 1 signal. Okay, now let's just change a little thing here. Let's add a chlorine bond to this side and a carbon bond to that side right there. So these 2 hydrogens have a carbon on this side and a chlorine on this side. But these hydrogens only have a bond to carbon. That means they are electronically different because of the types of bonds associated with the carbon the hydrogens are bonded to, and gives rise to two different signals. Okay, let's extend that even more. So just like on the first one right here, these right here, this gives us one signal because we only have 3 hydrogens bonded to an oxygen. Okay. Now, this one is different than that one because we have 2 hydrogens bonded to an oxygen, and then it's also bonded to something that's a carbon. So that's a different signal. And then our last one here is going to give us another signal because it's the only one bonded to another carbon with 3 hydrogens on it. So that's what we mean when we look at number of signals. They have to be chemically or electronically different to be different signals. Okay. Now, this can get tricky if you're trying to draw things in shorthand. So, for example, when you have cycloalkanes or double bonds, you want to draw them out flat so that you can see whether or not they're equivalent. For example, if you just drew this right here, you're going to say, oh, well, these are equivalent to each other, and then this hydrogen's different. And that would not be right because these hydrogens are different than these hydrogens are different than that hydrogen because these are close to the chlorine, these are far away from the chlorine, and this is completely different because it's bonded next to a chlorine. So make sure you draw out your cyclohexanes. And likewise, your alkene here, if you just drew it like this, you'd say, oh, well, these 2 hydrogens are exactly the same because they're over there. Well, no, they're not, because this hydrogen is close to here, this hydrogen's close to here, and this one's furthest away. 3 different electronic configurations. Therefore, we get 3 different signals for that compound. Okay, so let's do a little exercise here and think about the first one right here. How many different types of protons do we have? Remember, this is a methyl group here. Oops. This is a methyl group here, and that means there's a hydrogen back here. Okay, so how many different types of hydrogen peaks should we get for this first compound? Go ahead and type your answer in the chat room. Now we're looking for, look at a couple bonds over, several bonds over, to see if they're the same or different. Nobody? Nobody's going to guess? Okay, let me help. Right here. Okay, I'm going to say that these hydrogens and these hydrogens are identical. Because if we look at it here, we got bonded to a carbonyl, bonded to this, bonded to here, bonded to a carbonyl, bonded to this. So if we go from this side here and this side here, we see the same types of bonds each way. So that's going to give rise to one signal here. So the next thing we have is this is its only hydrogen that's like that. So that gives us our second signal. And this methyl group is going to give us our third signal. So we should see 3 signals for that compound. Okay. All right, now let's do a hard one. How many signals do we have for this compound here? Come on, somebody's got to tap in the chat here. There's 16 people out there. Is my chat working? Okay. All right, there go. All right, a couple more answers. All right, even though these hydrogens are shown with their wedges and stuff, the answer is correct. 1, because they are all equivalent. We're looking at the connections of the bonds, not just the, the shape of the bond. Okay, so now let's do this one here. How many types of hydrogen do we have in that compound? All right, chat room. I know at least 3 people are listening. So, all right, there we go. That is true also, because if we look at the connection here to connection here to connection here, they are equivalent no matter which way you draw your lines, they are all in that same kind of configuration to each other. So again, the answer is correctly 1. Okay, so for this last one, I will show you that these are different than these because of the through space proximity here and the angle. That through space proximity does change things, and so that makes the A different than the B, and because they're both as far away from that chlorine as possible. And then this one has to be different because it's closest to that chlorine. All right, and in this case here, we're going to see the hydrogens attached to these 2 carbons be 1 signal. We're going to see the hydrogens next to that a 2nd signal. And we're going to see these right here give us our 3rd signal. And just like that, also, we showed you that this one's going to give rise to 3 different signals because of that through space interaction. Okay, so that is equivalency. So go ahead and practice equivalency on a couple different compounds. And once you start seeing it, it's going to be very easy to recognize the equivalency. All right, now let's talk about intensity. Intensity really doesn't mean the height of the peak. It means the area under the peak. So what we do is we do what we call integration. We basically integrate the area under the curve. And so we get what we call an integral. And it's this, kind of, if you remember your calculus, it's this little thing that looks kind of like this right here. And it's just basically saying no signal, and then there's a huge rise in signal, and then the signal stops. And so that integration is a linear representation of the area under that curve. And so if we take the area under this curve, and it just measures as an arbitrary number of 333, and we measured this one to be an arbitrary number of 1,000, and we divided the 2 from each other, we could see that this is equivalent to 3 hydrogens, and this is equivalent to 9 hydrogens. Also notice, look, these are very nice, clean single peaks, okay? And it's because we don't have any hydrogens within 3 bonds. We only have a hydrogen within 4 bonds, so we do not get any peak-to-peak splitting. Okay. So the integration is probably the easiest thing, but it tells you a lot of information about, oh, this peak has 2 hydrogens on it. This peak has 1 hydrogen on it. This peak has 3 hydrogen on it. It'll help you identify where the peaks are, sometimes just by the number of protons in each peak. Okay, now we have to look at chemical shift. Now, chemical shift is all about how far away from our internal standard we're going to be, okay? So in this case here, we have TMS, tetramethylsilane, and I'll show you that structure in the next couple slides right here. And so the shift to higher numbers from that internal standard gives us information about what things are bonded to, okay? So in the case of this right here, methanol, we see that a carbon bonded to an oxygen is going to be shifted up to around 3.2 ppm. And the hydrogen on the bonded directly to an oxygen is actually going to be shifted up to around 4, right there. So just those positions tell us something about the chemical structure, okay? So, and the cool thing is, because we use our internal reference, it doesn't matter what type of machine we have, we're always going to get that same number of ppm, because what we're looking at is the frequencies observed and the reference versus the spectrophotometer. So in the case of a very low frequency material, the actual frequency is taken into account. So your ppm takes into account, no matter whether you have a 60 hertz NMR or a 300 hertz NMR or a 600 hertz NMR, it will always give you the same shift in parts per million. So that parts per million is equilibrated for different types of materials. Okay, so let's talk a little bit more about TMS. Okay, so TMS is a great internal standard. It tends to be non-reactive, and It turns out that by measuring lots of things, almost everything is shifted above this. So we have hydrogen on a carbon that has this carbon-silicon bond. Okay. So silicon's a little more electropositive than carbon. And so therefore it's pulling a little bit of the electron density away from here, giving us our lowest shift for most common organic compounds. Okay. And so these hydrogens are by convention set as our standard of 0 ppm. So you always have a little bit of TMS in the solution, so you giving you ppm. So, but what does that tell us about chemical shift? Chemical shift is all about the electronic environment around those hydrogens we're seeing, right? So what could cause that stuff to shift, okay? So the idea here is that the electrons in our bond, our electrons around our hydrogen here, are either going to be more intense or less intense based on whether or not those electrons are being pulled away by a more electronegative atom or a less electronegative atom. So let's say we had something like, in the case of this TMS here, where actually the silicon is actually donating electron density to the carbons, which is donating electron density to the electrons around this hydrogen. Okay, so what that means is that we have more electrons around that hydrogen, that proton in that hydrogen, and therefore it shields the nucleus from that electromagnetic radiation. So that's why we call it shielded, is that one where it has more electrons kind of fending off that magnetic field. Now, if by contrast you had something that pulls electron density away, like this fluorine, it's a very electronegative and it's pulling electron density away from that carbon, meaning that there's less electrons around that hydrogen and the nucleus of that hydrogen, that means it is now de-shielded. It will go up, it'll get to higher and higher ppm numbers. Okay. So we use the phrase shielded and de-shielded to tell us where it'll be on the spectrum. Okay. So the other way we say that is upfield versus downfield. Okay. Upfield is getting more and more electron density around those hydrogens and are more like TMS. Okay. So for example, straight chain hydrocarbons are really low. They're around 1. And so we can see them being that they have very nonpolar bonds and they have the amount of the most reasonable amount of electron density around those hydrogens, and therefore they are closest to 0. As we change that, as we put them near electronegative atoms or things like carbonyls, that means those are going to be pulling electron density away from them. So in this case here, we have the more electronegative oxygen pulling electron density away directly from this carbon, and they get shifted upfield. I'm sorry, downfield. They get shifted downfield. They're shifted away from 0 because that electronegative atom is bonded next to those hydrogens. And likewise, this is an electropositive atom. It's pulling electron density away from them as well. Now notice that it's not the same as oxygen, but it's still shifted downfield from where we would find them if there was no carbonyl and there was no oxygen there at all. Okay. So when we think about downfield, think of increasing numbers of ppm. Upfield is closer to 0. Okay. So different functional groups will shift you different ways. But you can really imagine that if you had just ethane or propane, something very hydrocarbon-like with nonpolar bonds, you're going to see those down here because they are the nonpolar bonds and therefore they are shielding it from the magnetic field. Okay, so let's see about where these things show up and how they shift around a little bit. Okay, so I said before that the hydrocarbons are the ones that are going to be shifted down closest to 0. And as it turns out, it's even cool that the CH3s are actually at this end The CH2s are in the middle here, and then the CH1s, just the CHs, are at the higher end of this. The more hydrogens you have on that carbon, the further upfield they're going to be, the closer to zero they're going to be. Okay. And then our CH2s that are near something, we're going to see them shift between 2 and 3. So notice these are all kind of electronegative atoms, but not really electronegative atoms. Now, if we go to really electronegative atoms like halogens and oxygens, they're shifted up even higher, the 3 to 5 range. Okay. Now we have an alkene. An alkene has a pi bond. It has a different hybridization. So when it has that different hybridization, it's shifted up higher here. Okay. Notice that acetylene is down here. The terminal alkynes are down here. So it has pulled enough electron density to form the double bond. And now that it has that second pi cloud, it shifted it back a little bit. So look at it that way. As we add a benzene ring, that resonance of the benzene rings will kind of pull it up a little bit more. Then we have aldehydes right here, about 10. And the only functional group we typically see above 10 are carboxylic acids, the hydrogen, the acidic hydrogen on that. Okay. So notice this is a really broad band for nitrogen and oxygen. It goes all over the place. If it's an ester, it's going to be one place. If it's a secondary alcohol, if it's near something electron withdrawing, if the hydrogen has more than one, nitrogen has more than one hydrogen on it, it shifts around quite a bit. Okay. And so that is a little bit harder to identify sometimes. Okay. Now, the last functional group I want to draw your attention to is this carbonyl right here. So this carbonyl is right here. It's shifted up just above the hydrocarbons, but just below things like ethers. So it's going to be that intermediate one that shows up in that 2 to 3 zone. We're going to see as you can start predicting where different functional groups will show up because, oh, this CH2 is next to a carbonyl group. This CH2 is next to an oxygen. This hydrogen is on an aromatic ring. You're going to start to pick out the zones where you expect them to be. All right, so we'll do a little bit more about these different zones here, but think the more hydrocarbon-like, the closer to zero. Things with electronegative atoms on it are starting to move up, although carbonyls and less electronegative atoms are in the intermediate range. Alkenes will go in the 5 to 7 range, aromatics are above that, and then carboxylic acids are at the top. Okay, questions about shift before I move on. Okay, so remember we had 4 things that we look at. The number of signals, the integration under the curve so we can know the number of protons, the shift. The shift tells you what those hydrogens are near, what functional groups those hydrogens are near. And then we have to do the last one, which is splitting. Okay. So in splitting, we have 3 rules for splitting. Okay. First rule, equivalent protons do not split each other. Okay. So if you have 2 CH2s or 2 CH3s next to each other that are equivalent by our electronic equivalents that we picked out in number of signals, then you get 1 peak for those. You don't split them at all. Okay. Okay. For, let's say you have non-equivalent hydrogens nearby within 3 bonds. Okay. These are 3 bonds, 2 to 3 bonds. So imagine you have a carbon and a carbon, a hydrogen, let's do an X and a Z so that they are different. You have to be 2 or 3 bonds away to split. If you're more than 3 bonds away, they do not count. Okay, so 3 bonds, 2 to 3 bonds is the rule for splitting. Now, in that we have what we call the N+1 rule. Okay, 1 is for the hydrogens that you're talking about. So we get 1 signal for those hydrogens on that atom. Okay. N is the number of non-equivalent protons within 3 bonds. Okay. So for example, if we had a compound here that has one hydrogen. Let me actually redraw up here. If we had a compound that had, let's do this one. Oh no, where to go? Close, there we are. All right. Hydrogen, hydrogen, and a chlorine. Let's put that back. Okay. So we know we have two different types of hydrogens. We have these hydrogens that are equivalent, and we have these hydrogens that are equivalent, right? And these red hydrogens here get one signal for those two hydrogens. Okay, so that's our one. But there are a total of 1, 2, 3 hydrogens within 3 bonds of that set of hydrogens. So that's the N. N is the number of hydrogens that aren't equivalent that are within 3 bonds. So in this case here, we have a 1 for this signal and a 3 for this signal, which means we're going to get 4 peaks for our splitting. Okay, our 1 proton has been split into 2 protons. Sorry, our 1 proton was split by those other 3 to give us a total of 4 lines in our peak. Okay. And then splitting observed for non-equivalent protons on the same carbon or adjacent carbons. Okay, so which means that you can have something like Cl, H, H, H. And so, like I said, it's 2 to 3 bonds. Because we already identified that these are 3 different kinds of protons because of their interactions with things that are nearby, that means that this hydrogen is going to be split by this hydrogen and that hydrogen. This hydrogen is going to be split by both of these hydrogens because it's on there. So we have to also look for hydrogens, non-equivalent hydrogens that are even on the same carbon, but adjacent carbons if they're 3 bonds or less. Okay, so does everybody understand our N+1 rule? 1 is for the peak, the N is for however many hydrogens on either side of that peak. So you could actually have, 6 hydrogens on either side of that peak. You can have 9 hydrogens on either side of that peak sometimes if you have 3 methyl groups on a single peak. So let's look at that a little bit. Okay, let's go into more detail. Okay, rule 1 is that our non-equivalent hydrogen split the other hydrogen. Okay, so in the case of this compound here, we have 1 hydrogen on this carbon and then a whole bunch of R groups, and then a 1 hydrogen on this, and they are different R groups, so they are electronically different. Okay, so if we're not going to count, we're going to say these are R groups with like fluorines or something on them, so we don't have to worry about it. So this hydrogen gets 1 peak for its being there, but this is not equivalent to it, so this gets a second. This is the 1 hydrogen nearby. So that means we're going to end up with 2 peaks, 1 plus the 1 hydrogen nearby. Okay. So the reason they split is because they are different. They are non-equivalent, and because they're non-equivalent, they have different magnetic fields that they have, and that's what causes the split. The fact that they are magnetically and electronically different, that's what causes our split. Okay. Okay, I'm going to stop here at rule 1 because it's 10:50 and your time is valuable. So I will go ahead and upload this there, and we'll start here on rule 1 on Wednesday. Okay, go ahead, and anybody who wants to hang back and ask questions, go ahead.
Yeah, I've got a question.